Good morning, ladies and gentlemen, esteemed faculty members, and dear students. I am Dr. Mekhla Mukherjee, reader in the Department of Periodontics. Warmly welcome you all to the second day of the which has been made possible through the funding received under the FIST scheme. But before we begin today's, I would like to highlight that March 20th is marked as the World Oral Health Day. Our students Our students, under the guidance of the Department of Public Health Dentistry, have put in great effort to make this day special. I would request everyone to kindly watch the video, and kudos to our students for creating the character Molar Bear. In my heartfelt congratulations to the entire team, to all the faculty members of the Department of Public Health Dentistry under the leadership of Professor Dr. Shantanu Sen sir. I would request Professor Dr. Shantanu Sen sir to come on the dais along with the students who worked really hard to create this. I would call upon the stage Meghna, Fiza, Manmit, Kankana, Adrija, Oshik, Yash, Aloy, Hoimoshri, Mansha, Shubham, and Aditya. I would request our principal sir, Professor Dr. Jayanta Bhattacharya sir, and our hospital superintendent, Professor Dr. Soumitra Ghosh sir, to please come on the dais for a group picture. Moving forward, let me give you a brief overview that Gnidsr is currently a recipient of the esteemed DST-FIST grant under the leadership of our respected principal, Professor Dr. Jayanta Bhattacharya sir. Our institution has received 50 lakhs for acquiring advanced research equipments including a spectrophotometer, a 3D printer, and a micro-Vickers hardness tester. These facilities are now strengthening our research capabilities and opening new avenues for innovation in dental sciences. Today, we are privileged to have with us Dr. Sugato Ghosh, Assistant Professor and Head, Center for Renewable and Sustainable Energy Studies, JIS Institute of Advanced Studies and Research. I would request Professor Dr. Paramita Mojumdar Madam, Head of the Department Conservative Dentistry and Endodontics, to come up on the dais for the welcome address.
Thank you, madam. Good morning. So today we have gathered here. This is the second orientation session for something that we have been hearing very often, DST-FIST and DST-FIST grant. So what is it? For the uninitiated, I would like to say that it is a Department of Science and Technology, Government of India initiative, which is giving funds to the universities and higher educational institutes to upgrade the research infrastructure. So DST is Department of Science and Technology. FIST is the Fund for Improvement of Science and Technology. So we have received a grant with the blessings and guidance of our management, leadership of our principal, Dr. Jayanto Bhattacharya, and the initiative of our hospital superintendent, Dr. Soumitra Ghosh. Now this was the vision. The equipment are here, and today we will hear from our esteemed resource person and expert, Dr. Sugato Ghosh and Mr. Sanjay Mishra, about spectrophotometer. So to name the equipment, last day we had a session on 3D printing. Today we will have a session on spectrophotometer and its applications in dentistry. And we have another equipment which is the hardness tester. So this is the laboratory under the DST-FIST project, which is a premier project of the Government of India, which is housed in the adjacent building, which is the DST-FIST lab. So as I said, this was the vision of the management and the leadership of the local administration GNI DSR. This is how far we got. But now we have to fulfill the mission. So what is the mission? Equipment will mean nothing if we do not put it to use. For the MDS dissertation thesis, it is a routine affair. We as faculty members, we have this responsibility on our shoulders to understand about the equipment and put them to good and greater use. So with these few words, I would like to welcome you all again to this orientation session, and we all hope that we will have a very enriching session. And I think, Mekhla madam, there will be an open session for the question answers, if any. Thank you all very much.
I would request Paramita Madam to please stay back on the dais for the felicitation ceremony. I would request our principal, Professor Dr. Jayanta Bhattacharya sir, to please come up on the dais to felicitate Dr. Sugato Ghosh. Okay. I would request Mr. Sanjay Mishra to please come on the dais for the felicitation ceremony. Dr. Sugato Ghosh, we welcome you again on the behalf of our institution. The stage is yours.
Okay, okay. Hello, hello. Yeah. So I'm really happy today to be here and to present something about the spectrophotometer. And this is, first of all, I would like to congratulate the entire GNIDSR team uh, who have received a prestigious grant uh, from DST-FIST. So I'm really happy to hear also that we have received a lots of equipments which are very much important in our regular research life. So today I will try to give some illumination about the spectrophotometer. Uh, it's a brief overview about the spectrophotometer. What is spectrophotometer? What is the basic principle of spectrophotometer? And what is the basic physics basically behind the spectrophotometer? And thereafter, how we can use in several research work. That I would like to mention today. So first of all, this is the sequence of my presentation. That is the basic physics of absorption. That is spectrophotometer. The name itself says that spectro. That means there should be some spectrum, and photo means there should be some photon, whatever is coming, and meter means obviously measurement. So spectrophotometer, a range of wavelength we will use here to measure uh, some output from the materials or anything whatever is there. So how we can measure and what is the physics, that I would like to say. And thereafter spectrophotometer working principle, that what is spectrophotometer, what are the different parts of the spectrophotometer, how we can use in our regular work, and obviously we will go for some examples. We will try to say something about the real world, what is happening, and in parallel we will try to say something about the dental work, what we are doing in our regular research. So here I would like to say another one thing, that I am already associated with several projects with GNIDSR, and we are trying to develop several instruments for the dental use. So first of all, the basic physics of the spectrophotometer. Spectrophotometer means, obviously I have told that it is about the absorption of light or anything, wavelength. So we know that what is sunlight. Sunlight, whatever is coming from the sun in our earth, in our mother earth, that is the sunlight. That is, we can say that there are several wavelengths of lights are coming, actually starting from the gamma rays to radio and TV, that is gamma ray, X-ray, UV, visible, infrared and microwaves. These are the series of lights, whatever series of actually wavelengths. We cannot say this is the entire light. This is the wavelength, and among these only a small spectrum, that is the 400 to 700 nanometer, which we say that is our visible spectrum. Beyond that, it is UV, ultraviolet. We do not want this come from the sunlight. And third one is IR. IR means infrared. Infrared means that is totally the heating. The whatever the heat is there, that is the IR range. So we can see that wavelength is changing, and accordingly for every wavelength there is some energy is coming. Energy is coming, that is in terms of photon. So the photon energy is coming, whatever we need. Primarily we can say that the photon energy from the earlier days, it started to receive by the trees to produce the energy there. But here we will see that how the technology we can use here to receive the photon energy and to illuminate something different. So we can see that the energy is increasing, and what according to the wavelength, and higher energy photon, uh, that is the blue light for the wavelength of visible. We can say that higher energy photon is for blue light and lower energy photon for red light and something like this. So the light whatever is coming, that is actually electromagnetic induction. So a spectrum actually. So this is the energy of the photon. So we can measure for each and every cases, what is the photon energy for each and every wavelength. So there is a very easy formula is there. E is equal to hc by lambda. Lambda is the wavelength. So this is the relation between the photon energy and wavelength. So we all have learned in earlier days, but maybe some of us have just forgot about these things. So I will try to recap everything. So this is the E is equal to hc by lambda, h nu actually, that is hc by lambda. H is the Planck's constant and c is the velocity of light. So speed of light or velocity of light. So from here we can easily measure what is the energy of the photon. So and whatever the energy, why I am telling about the energy of the photon, that is we need to absorb the energy. How we can absorb that energy, that is our main motto, to understand what is happening inside the spectrophotometer. So yeah, so what happens if energy falls on a material? Of course there is something happening. So what is that? So energy means, obviously if we think about a material, that primarily goes about the atomic structure. What is the atomic structure? That is, at the center there is nucleus, and surrounding the nucleus the electrons are so at the center there is the nucleus, and electrons are moving uh, around the nucleus, and there is also a lots of energy states. We can say that energy states like SPDF, in this way we can say. And finally we can say that there is a band, that is the valence band. Valence band is the last band of the electron, where the electron is available, last band where the electron is available, and thereafter also some bands are there. That is normally not, we do not use, normally it is not used, but sometimes when the electron is in excited state, they jumps from valence band to conduction band. So that is when an electron jumps from the valence band to conduction band, in that time we can say that yes, the electron is free to do something. It can move here and there, and it can do anything. It can absorb the energy, and then it will move from the valence band to conduction band. When it is in valence band, then it is bounded. But thereafter, when it is going to the conduction band, that means it is free electron. So it can move here and there. But sometimes we say that this is metal. Electron can, current can flow through this one very easily. And this is non-metal, that is, this is insulator, the current cannot flow. And something is there in between the metal and insulator, that is called semiconductor. Semiconductor means the current may flow or may not flow based on the conditions whatever we are applying. So for metal now, now if we see, yeah. Now if we see about the metal, what is the position of valence band and conduction band? It is overlapping to each other. So valence band and conduction band overlaps. That's why there are lots of free electrons are available. So when there we are trying to what can I say, that yeah, when we are trying to make some flow of electron, that means flow of current, whenever we want, the current can flow through this, because as the conduction band and valence band, that is overlapping to each other, obviously the electrons whatever is available in the valence band, that is already moved to the conduction band. So we can easily say that there is a lots of electrons are available which are actually free electrons. So if it is free, then it can move here and there. And secondly, what is the condition of semiconductor? Semiconductor industry is actually the main thing from we are using the mobiles, we are using the laptops, whatever we are using, semiconductor is the basic and main thing of this, because we can apply some potential to make it conductor, and whenever we do not need to do something, then we will make some another potential which will make it make it towards semiconductor. So it is in between metal and semiconductor. So whenever we require, we can make it metal. That means conduction is possible. Whenever it is not required, then we can make something arrangement where conduction is not possible. So we can control. So this is the main thing of the semiconductor, for which we are using in our regular life. That is, whatever the chips we are using, we are saying that this is very small chip, whatever things, VLSI, ULSI, very large scale integration, ultra large scale integration, everything is depending on the semiconductor. So, and third one is insulator. There is a huge band gap. So in case of semiconductor, there is a band gap, but the band gap is very small, so that we can easily move the electron from the valence band to conduction band if we give some energy, external energy, and whenever is not required, we will remove that energy. The electrons will again move from conduction band to valence band. And third one is the insulator, where you can see that is the band gap is so much. If the band gap is so large, then what will happen? That is it is not possible to move the electron from valence band to conduction band, whatever the energy we can give from outside. So that is the difference between these things. But why I am telling about these things in respect to the spectrophotometer? Because of course spectrophotometer, in case of spectrophotometer, we want to measure the movement of electron from one part to another part, from one band level to another band level. So whenever we are trying to move the electrons from one band level to another band level, then what we need? We need some energy. Who is giving the energy? The spectrophotometer. Spectrophotometer is giving the energy in different levels, and we are the material is absorbing, and thereafter it is giving the output, and we are getting the output from the detector of the spectrophotometer. So this is the basic, what I will explain again. Yeah, absorption of energy. Absorption of energy means, that is, I have already told that absorption of energy in a material, that means absorption of energy in a material by the available electrons. So by the availability of electrons, the electrons will move from the lower energy state to its higher energy state. When it will move from lower energy state to higher energy state, what will happen? That it need to absorb the energy whatever is required. But my question is that whatever the energy will come, will it receive all the energy? No. Why no? Because we have said about the level of band structure, that is, one is conduction band, one is valence band. These things are available, but in between the valence band and conduction band, is it possible that the electron can stay? It's never possible, because to stay electron, to move a electron from one level to another level, they have to get some energy levels. That means I can stay here, I can stay upwards, I can go upwards and stay there, but I cannot stay in between this, then I will fall down. So that's why same thing happens for electrons. The electrons can move only from one band to another band. So whatever the energy is coming, what is happening for that? If the energy, I have told about the energy of the photon E is equal to hc by lambda, h nu. So that is the lambda is the wavelength. So the wavelength of the energy, from there we can calculate what is the amount of photon energy what is the value of the photon energy. So you can see that one is the VB is the valence band, and above there is the conduction band CB. So one electron is moving from VB to CB. That means they need the amount of energy that is EG, band gap. They need the energy of band gap, minimum energy that is required. Then only it can move from here to there. So whenever the EPH means the, first of all, that is photon energy, calculated photon energy, and EG is the band gap. Is the band gap, that is gap between the valence band and conduction band. So if some electron needs to move from valence band to conduction band, how much energy is required? That is EG. And what is the energy is falling? That is EPH, that is photon energy. So the photon energy, if the photon energy, amount of photon energy is less than the band gap, then what will happen? If it is less than the band gap, then mostly transmission of the light will happen. That means we will see it is transparent. The material is transparent. And when it is just EG is EPH is equal to EG, that means photon energy is equal to the band gap. That means it will, the electron will receive the energy, it will absorb, and then it will move to one band level to another band level. And third one is that it may be that E is greater than EG. That means photon energy is much higher than the band gap energy. So in that case, it may accept the energy and it will go to the higher state of conduction band, and then it will release the extra energy and it will come to the lower state of the conduction band. And whenever the opposite thing will happen, that means the photon, that means the electron will move from the conduction band to valence band, reverse back. That is called, actually in our terms it is called recombination. This is called generation and that is called recombination. So when recombination happens, that means the electron have to release that amount of energy. So this is the basic phenomena. And of course, there are some defect levels are also there. That means if there is some impurity, if we are trying to say that the tooth, that is enamel dentin, these are fragile. That means there is some impurity maybe that has been developed inside. So that means the property whatever was there for the enamel and dentin layer, it is degrading. It is degrading means, how can I say from the prospect of material, we can say that several defect states have been generated. That's why the whatever the property was there for the enamel or dentin layer or something else, so in that case we can say that the due to the defect states, they creates some extra energy level that are called sub band gap energy levels or trap levels. The electrons may move from one that is from the conduction band, valence band to conduction band. Otherwise, it can move from the valence band to trap levels, and from there it can move again to the conduction band or come back. So there are some extra levels that we can also detect by the spectrophotometer. So if there is some levels, that in that case also absorption will take place. So now I am coming to the spectrophotometric analysis. So whatever I have told till now, that is atomic spectroscopy. That means atomic spectrophotometry analysis. That means if there is atom, in that case what will happen? Already there are bands, band gaps, and electrons will move from one to another level, and it will come back. It will accept and release the energy, and by this way we can find out something. And of course, in the molecular spectroscopy, I am not going into details about this, but that is, we know that pi band and the sigma all are available there. Whenever the electrons are jumping from sigma to pi, pi to sigma, pi to pi star, in these levels, there will also be some signature peaks will also be available in case of spectrophotometry. And now when the energy, that is light energy, it is traveling through a medium, what is happening? What may happen? One is reflection may happen. Reflection, obviously, from the surface it may reflect. Another is transmission. Whatever the energy is not absorbing and not reflecting, that will be transmitted. So this is another. Third one is the most crucial thing that we say, that is the absorption. What is the absorption? Already I have discussed, and that is the electrons. The electrons will accept the energy and the absorption will happen. So this is reflection, absorption and transmission. And we need to understand these all phenomena. And now the question is it possible to understand which level, which wavelength of light is getting absorbed, and what is the amount of absorption? First of all, how much it is absorbing, and second one is that if I can say that there is a material, I am sending a light, that is white light. So is it possible to understand that whatever the absorption is there, whatever the transmission is there, and whatever the reflection is there, if we want to quantify in each and every wavelength level? So that is not possible at all, because the white light, it's a combination of all the seven lights we say, that is actually the combination of 400 to 700 nanometer wavelength. So if we want to quantify what is the amount of light required, amount of light it is absorbing, which wavelength it is absorbing, and according to the wavelength, what will happen? That whatever the band gap, what is the position of the band levels, we can understand these basic things from this. So this is the so therefore we need to understand that which wavelength of light is getting absorbed and whichever is getting transmitted. So for that, what is need? We need the diffraction of light. So here I have explained the visible light diffraction. Visible light diffraction, obviously there is a prism. We have read this type of experiments in our class 8, 9, 10 standards, but the thing is happening again here. The thing is happening again. That is, we need to distinguish, we need to differentiate all the wavelengths of light. What is, that is the from the left side, the white light is coming, and after dispersion we are getting distinct red, yellow, orange, red, orange, RY, all the 7 lights we are receiving. So this is the basic phenomena of spectrophotometer about the source. So spectrophotometer means there should be a source of light, and is it possible to get all the light sources? It is not possible. So there should be one source, that is That is actually spectrophotometer. What does it do? That is the whatever the light is coming, that is the light in, that it will measure first. We can measure it very easily. So these are the spectrophotometer basic working principles. Light source, thereafter monochromator, third one is the sample holder, and fourth one is the detector, and finally is the output. So monochromator, already I have said that tungsten or halogen or xenon, these are the light sources, and monochromator obviously prism or diffraction grating which separates the light into individual wavelengths, thereafter sample holder to hold the sample, and finally the detector. And I have told about the monochromator, which was single monochromator. We can also use we can also go for the double monochromator, that is for much accurate measurement we can go for this type of double monochromator sources. So here you can see that one time it is the light is diffracting, and again that diffracted light is going to the second level, and again further diffraction is there, and from there we can measure something very precisely. And another is double beam spectrophotometer. Whatever I have told, that is that was about the single beam spectrophotometer, and here we can see that there is a sample and there is of course a blank range also to measure something if there is in between the path. For that, double beam double beam spectrophotometer is also available, where you can use some chopper that the monochromator output sometimes will go through the sample and sometimes it will go through the mirror and through the blank sample, and finally we will get that whatever the detector is detecting. So there is a big calculation. From there we can understand that how the double beam spectrophotometer works. And another is integrated sphere. Integrated sphere means we can say that what is the difference between the integrated sphere and normal linear optical phase path. That is, in case of linear optical, just direct transmission is possible. Whatever the direct transmission is there, it can easily detect that one. But if there is something reflectance from the upper surface, then it cannot be possible to measure that one. For that, we can use the diffused reflectance. We can measure the diffused reflectance and of course the transmission through the integrating sphere. And UV-Vis NIR spectrophotometer, what are the basic applications? In case of pharmaceutical analysis, in case of environmental monitoring, food analysis, material science, chemical analysis, everywhere, in each and every aspect, our first measurement is the Vis or UV-Vis analysis. Whatever the materials is inside, we cannot understand without knowing these things. For pharmaceutical analysis, the concentration of some chemicals, what is the purity, how can we measure that one? Only the first step, the basic step is the UV-Vis analysis. From there we can understand. And environmental monitoring, that is pollution, air pollution, water pollution, whatever several dyes, if the dyes are there inside the water, how can we understand, how can we measure? Everything can be understand primarily by using the UV-Vis analysis. Thereafter, food analysis, material science, whatever the materials we are developing, first our step is to go to the UV-Vis and check what is the basic band gap, what is the band structure, what is the position of the bands, and how the electrons are moving from one to another. These all things are required to measure. And this is actually solar cell spectral analysis. This is one example. Whatever we several times we have done in our laboratory, that is the spectral response. We are saying that the solar cell, which is absorbing light, what type of light it is absorbing, in which wavelength it is absorbing, in which wavelength it is not absorbing, everything we can understand. That is, here there is a graph for the wavelength of 200 to 1000, approx 1100. So here we can see that entire spectrum it is absorbing by the solar cell. That is the basic requirement of these things. And another is typically spectrophotometer response, that is dye degradation. In several cases, dye means some poisonous materials which are available in the water medium also. So that we can measure from the spectrophotometric analysis. Here you can see that this is a result of dye degradation. Dye degradation means you can see that there is a huge peak. Initial peak was much bigger, and whenever according to the time we are giving some treatment on the water and we are getting some output, that is continuously, it is time to time it is degrading. That means the poisonous material is continuously degrading. So from there we can understand that concentration of poisonous material is also reducing. So by this way we can say that the dye is reducing, and it is converting to better something better which is not poisonous. So by this way we can understand what is the spectrophotometric response. And in medical use, this is actually the pulse oximeter, which we measure continuously to understand what is the oxygen level of our blood. So this is the response actually whatever the pulse oximeter is measuring, that is that we can say a very small spectrophotometer. Primarily we had to measure all the wavelengths of lights for the oxygenated blood or deoxygenated blood. We have to measure all the wavelengths of lights, what is the response, and finally we have found that there are two wavelengths. One is red, that is 660 nanometer, and another is infrared, that is 920 nanometer. These two wavelengths are the key wavelength where we can measure the value of the oxygen saturation of the blood. That is, you can see that one is for carboxyhemoglobin and another is for oxyhemoglobin. You can see that at 660 nanometer there is a distinct difference between the absorption of carboxyhemoglobin and oxyhemoglobin, and second one is at 920, there is a totally opposite response. That is, in case of 660, that is oxyhemoglobin is absorbing much more, but carboxyhemoglobin is not absorbing such level. But the opposite phenomena is happening, that is for IR 920 nanometer, the oxyhemoglobin is absorbing much more with respect to the carboxyhemoglobin. And there is a ratio, there is of course a ratio in between these two. What is the amount of response in 660 nanometer and what is the amount of response in 920 nanometer? And by measuring the ratio, and there is of course a calculation, we can say that yes, this blood is this blood has the level of oxygen in 97, 98, 99 or 40, 50, whatever is there. The only the measuring unit is the ratio. Primarily we had to measure all the wavelengths. Thereafter we found out that these two wavelengths we can use, and in our normal pulse oximeter we have these two wavelengths of source, and from there we are measuring the concentration of blood. One side is source and another side is detector. That's why we can say that pulse oximeter has some red light is there. So that is the 660 nanometer wavelength. Apart from this, there are lots of applications are already available. These are the in whatever the tissue culture, whatever the other things are happening, we have to first measure the pulse oximeter. We have to first measure the quantitative analysis. That means in what is the response level in which wavelength. From there we can understand that what is the amount of change in a normal case and abnormal case. So from there we can understand that what is happening inside the cell or everything. And here is the quantitative analysis. So if we want to measure some unknown concentration, there is a concentration of some liquid, we don't know what is inside. So first of all we will go for this one, that is the UVV spectrophotometer. There is a kinetic studies, that reaction kinetics, what is happening. Already I have told about that dye degradation, that is there is some reaction is happening and the dye is getting down. The wavelength in some wavelength the response of dye is getting down. So from there we can understand what is the amount of reaction, what is the reaction kinetics, everything we can understand by time to time. And so we can go for purity assessment, impurities detection, molecular identification, several things are there, and structural and physical data, functional group identification, conjugation status, everything, band gap measurement. I have told about the band gap, conduction band, valence band, and the gap between that. How can we measure that? Everything is possible to measure by these things. And color and quality assurance, I think sir is there. He will say a lot about the color and quality assessment. So I am not going in detail about this. and several dental cares are there. Early detection, diagnosis of various oral disease, cancer, precancer cells. How can we measure the cancerous cell? How can we measure the precancerous? How can we measure the good cells also? By this way, we can understand that yes, this cell may go for the cancerous zone or it is good cell. We can understand everything from the spectrophotometric analysis. And oral cancer, precancer, already I have told that detection of accuracy, everything we can go for. Here is an example that different absorption and reflection properties when exposed to specific wavelength of light, tumorous and precancerous tissues. There we can see that here the tumorous cells have grown, and from there we can find out that one is actually dark blue color and another is almost white color. So from there analysis we can find out that whether the cell is cancerous or precancerous or whatever the condition of the tumor, everything we can understand from these things. So but we cannot say that in a small time, and we need to elaborately describe if it is actually required. So enhancement of treatment quality, of course it will enhance if it is in chair side of the dentist, then it can easily enhance the treatment quality of the patient. So by this way, again I want to congratulate Gnidsr for getting this fund, and of course we will believe that several collaborative research work is going on, and we will do a lot in future and in between GIS, IASR and Gnidsr. So thank you.
Is there any questions? Yes, ma'am, please.
Is there anything which is available chair side?
Uh, yeah. Actually, I have seen, I have never used this type of equipments, but I have seen there are a small torch like equipments are available, which you can use and you can apply for the patient. That is, there will be a very small variation of wavelength. I think it will not be a large amount of variation, but small amount of variation it is possible, and I think you can, sir can explain that whether any small equipment is available which we can use. And another thing is that we can use spectrophotometer with several spectrophotometers are available, which are actually here you can see that the probe and everything is inside, and some spectrophotometers are available where you can measure the entire thing outside the box. So in that case we can also use that one.
Thank you, ma'am. Any other questions from the students? Okay, sir. Thank you so much, sir, for giving the time and effort to our institution to share your knowledge. It was really informative.
Thank you so much.
I would now request Mr. Sanjay Mishra to please come up on the dais to share his valuable knowledge on the machine spectrophotometer.
Hello. Good morning, everybody. I am Sanjay Mishra from J Instrument and Systems Private Limited, Mumbai. We are representing Konica Minolta Japan make color measuring instruments. And thank you, Principal Sir and faculty members for procuring the Konica Minolta spectrophotometer through us and giving us opportunity to serve you. So today also I will thank you to give your valuable time for my presentation on the color measurement instruments. So Sugato sir has already explained you very detailed uh, uh, color theory, how color is absorbed and how it is. So I will not go much detail into that, but briefly I will go through it. First, what is the why color is required to measure by the instruments, and then what is the methodology of using the instrument for measuring the color. So we'll first see why color is required to measure by the instruments. So when you visually observe the color, you say how the color is bright. Bright means whether it's a lighter color or darker color. Then what is the tone of that color? Means how saturated it is. It is less saturated or more saturated. Generally, we see the color visually in this terminology. So, how we perceive the color? For perceiving color by the human eye, you require three things. One is the light, second is the object of which you want to see the color, and third one is your eye. So, sir has already explained you that whatever we see by color by our human eye is only in the range of the visible region. And what is the visible region? Visible region is from 400 to 700 nanometer. Sir has already explained this phenomena. So visible light is very small part of the whole electromagnetic spectrum. The human eye can see only from the 380 to 780 nanometer. That is called a visible light. Sir has already explained you that when the light falls on any objects, what will happen? So first it will happen, there will incident and reflect into the perpendicular direction. That is blue light, that one, this one. So it will incident and reflect directly. And then what next it will happen? It will happen that light will incident and will speculate, means reflect in the same opposite direction, in the same way but in opposite direction. Then the transmission, the light will fall, and if your product is transparent, then light will pass through it, full light. Then the scattering, if your object is not fully transparent but slightly translucent, then what will happen? The light will fall and penetrate slightly because it is translucent, not fully opaque, and it will interact in between and then reflect. And another one, it absorbs. So light will fall and slightly absorb, and it depends what is the property of the material. So some light will absorb and some light will reflect. That is called a reflection. So these are four things are happening when the light falls into your objects. Either it will the incident light, specular light, transmission light, scattered light, or absorbs light. So why does an apple appears red? Because you can see this is our visible range starting from violet to red. In school we have learned that the visible light is a vigor, that is violet, indigo, blue, green, yellow, orange, and red. So violet is a shorter wavelength and red is a higher wavelength. So why apple is appear red? Because apple is red. So you can see the maximum absorption is happening in the red region, and all the other color is absorbed. So whoever is the maximum reflection, that color will you pursue, because apple is red, and so maximum reflection will be happening in the red region, and that is why we are perceiving the apple as the red. So likewise in other color also, if you see this in white, what will happen in the white color? All the color will be absorbed maximum, reflected maximum in the same proportion. So that is why this is almost flat curve, and since all the color has been reflected 100%, near about 100%. So that is why we see that particular color is a white, when all the color will be reflected 100%. And what will happen in the case of blue? See, you can see in the range, spectral range of blue, maximum reflectance will be in the blue region, and other color will be a less reflected. So that is why blue color is seen as a blue color. So how our eyes are perceiving the color, what is the scientific phenomena. All of the doctors you might be knowing much more than me, but uh, just a brief that whenever uh, light falls on any object, the reflected light is seen by retina of our eyes. In our retina, we have uh, many. In next, say we'll see the reflected light will be fall on the retina, and the retina will give the signal to the brain. And according to reflection, which you have seen earlier, it will show you what is the color. In next slide, so the image is projected onto the eye's retina, and then photoreceptor cell in the retina converts the light into electrical signals, and then optic nerves carry the signals to the brain, and information is recognized by the brain. So in our eyes, how we see the colors? In our eyes, they are called cones and the rods. Cones are responsible to visualize the color, whereas rods are for the, it can see only the whether it is brighter or darker. The rods cannot see the color. Only cones can see the colors. So in cones, we have the three sensor in our eyes. So long wavelength cones, visible medium wavelength of the cones, and the visible short wavelength of the cones, red, green, and blue. So these three sensors are there in our retina called a cone, and that is why we perceive the color. And if these cones are not working properly, then there is a problem in observing some color. Sometimes you might heard the blindness of the color. It means some cones are not working properly, so some colors are not perceived properly by particular that human. So when any already explained, so there is a physics, there is a psychology, physiology, and the psychology is involved during the observation of the color. This we have already seen in previous slides. So here in this slide, I will not go in details. We'll move it because. So now we have seen how our human eyes perceive the color. Then why you require the instrument to quantify or measure the color? If you don't have the any instrument to measure the color, what will happen and what is the problem in visual observation? So the visual observation by human eye is affected by many conditions: light source, background of the object, object size, viewer condition itself, and viewer's memory, and illumination and viewing direction. We will see briefly next, one by one next. So what will happen if you have a different light source? Suppose you have, sorry, you have the tube light, white light, and you are observing the apple. So apple looks like, color will be like this. But what will happen if you see the apple, same apple in the different light source. See, now this is the tungsten bulb. Tungsten bulb is already means itself having the some yellowish light. Tube light is having the white light. So that yellowish light also incorporated in the color of the red apple. So this apple may look differ from that white light. So there will be difference in the color when you observe the same color under sunlight or fluorescent tube light or incandescent, that is tungsten bulbs. And also the color will differ by human eye if there is a climatic condition change. If there is a sunny days or cloudy days or rainy season, in all these three conditions, the same color will look different. Also, there is the, if you see the same color in morning, afternoon, and evening, because there is the difference in intensity of the daylight. In the morning, there is slightly little less. In afternoon, it is more intense light, and in evening, it is very less light. So that also plays a very crucial role when you see the different color, same color in the from morning to evening. So because why we are seeing the different color in different light sources, because each light is having different spectrum, reflecting spectrum. Average daylight having almost similar light, but when you go the tungsten light, it is more reflected in the red region, whereas in fluorescent lamp it is almost a very abnormal light source. So let us see real life examples where we face problem in observing color. When we go in meat shop, they will put meat in certain light. They put certain lights, and we uh, we see it, and it looks good to us, and if we bring it to our home. What will happen if we bring in our home? It looks something different, because in our home it is a different light. You understand the challenge of the human eye observation of the color. Well, whatever it appears good in certain light in certain shop, it does not good so much delicious or good in when we bring it our home. Same thing happen. You can observe when the background, when the light is same and background is a white. You see, you can observe the color, and if you change the background, yeah. Now see, now this is the gray background. So how you can see the color? It is little bit lighter, brighter. But you will change the color to black background, darker background, your object also becoming darker. White, then it becomes a lighter. So background also plays important role in the human observation, visual eyes. Same thing, if you put the same yellow color in different backgrounds, this yellow looks little bit lighter, whereas in this background it looks a different color. Color is same, only background color is changing. Here also the yellow color and red color, the yellow color is same, but color looks different. And another challenge is that when you observe the same object in different angles, because if you change your eyes at different angles, then incident light and reflected light will be in different angles. So that also make a variations. So now I will not explain because this is related to some other. So there are the challenges of this visual observation. So what to do? Then it comes your instrument where it can give identical results to each human eye, because all this phenomena which we have seen that it is giving this challenge has been eliminated in the instrument. So everything is same. So all this condition memory itself, because if somebody memory means if somebody is tell you that the yesterday which you have bring us the apple, you bring the same red apple. So it all depends how you memorize the yesterday apple, what color apple you got. So it is not possible to exactly take today the same red color apple. So that is also a memory loss in human visual observation. So all those are the real life example which we have seen in the case of the meat. So these are the challenges during the visual observation, and that is why we are going for the instrument which can quantify the color. All this is a very detailed color measurement, so I will not take up this. Oh. So So, how the instrument has been developed to measure the color as per our human eye, so that the color which is perceived by the human eye looks same if the it is measured by the instrument. So, instrument measure data should be looks similar or give the similar uh, thing to our human eye. So, there are two types of the instruments, color measuring instruments. One is called a tri-stimulus type, and another is called a spectral type. So in tri-stimulus type, we have already seen that our eyes are seeing the color by the cones. In cones, we have the three sensors that is called red, green, and blue. So here in instruments also, they have provided X, Y, Z means red, green, blue sensor, which is equivalent to our human eye sensor. The scientist has studied it, our human eye response, and accordingly they have made a filter which can correlate or correspond to our human eye response sensors of red, green, and blue. And And what will happen in spectrophotometer? In spectrophotometer, they did not put the filter, but when the light falls, when the light falls, it splits into the spectrum from 400 nanometer to 700 nanometer, and then it calculates the XYZ value. So the spectrophotometer is the most accurate because you get the detailed spectrum analysis, whereas in tri-stimulus type of the color measuring instruments, you get only 3 sensors. You cannot get the whole spectrum data in the tri-stimulus type. So the instrument which you have procured, it is a spectrophotometer type. So so actually it is a R&D instruments where you can get analyze the detailed analysis of the color. So how a spectrophotometer? The instrument is already contained the spectral data of the light source, that is whether it is daylight source or our indoor light source like tube light or tungsten light. So all those illuminant light sources data has been inbuilt into the instrument, and as I explained you, it will calculate the spectrum and the spectral sensitivity of our human eye. When you calculate the RGB spectrum of human eye, it is like this only. And so the spectrophotometer also will correspond, means have the data of this spectrum, human eye spectrum response, and accordingly it calculates the color. So after getting the spectrum, it will give the tri-stimulus value, that XYZ. And then this tri-stimulus value, the color is measured in terms of L, A and the B. These 3 terms are there when you measure the color on the spectrophotometer. So we will see what is the L and B, how it represents the color in later slides. Yes. So there are many formulae to calculate the color. But nowadays, only L, A, and B color formulae are uh, recognized for the color measurement. Although these XYZ, LCH, Hunter Lab color or LEV, these are also there in your instrument. But to understand globally nowadays, people are following this L, A, and the B to calculate the color index. So So this is the LAB. So what is the L? L start from 100 to 0. The range of the L value is 100 to 0. So when there is a lightest color, your L value will be near to 100. And when your color is darker or darkest, then your L value will be going to 0. So when you measure the black color, your L value will be near about 0. But when you measure the white color, like your dental, everybody wants the very white dental color. So your dental L will be nearby 100. So more whiter you want, then L will be more towards the 100. Then A and the B is representing the color. So on the x-axis, this is the center. From center to right is the called plus sign. When you go towards center to the periphery, it will be more of the red value. So in this 0 to plus A, 0 to this one plus A, it is called a red. But when this 0 is moving in left direction, it is becoming minus, and you can quantify this minus A as the green color. So any green color, if you measure, it will give you the minus A. Red color is the plus A. Like that, the blue color. Blue, if it's a minus, if it is minus, it is blue. If it is a plus, it is a yellowish. So color can be quantified either plus A, minus B, or plus B. Same thing is represented here also. So LAB we can understand by this chart. This chart we have to keep in mind while understanding the color data of LAB. Another calculation not required to understand for another industries. Okay, so now here, just for example, which color looks redder? Anybody can tell which color looks redder, more redder in these two slides? Right hand side color looks more redder. More redder means we have seen in chart that red means plus A. So plus A should be more to that, right? So let us see the values. What is happening here? A value less, here it is more. Why? Because here you can see it is a L is going towards 0, less means it is darker. Here it going up, 56 means towards the 100, so it is lighter. And also your B value plus means yellowish, it is more yellowish than this one, it is lesser yellowish, plus B. So because of this phenomena, although visually you see this is the more redder, but it is not like that, because there's other components also. There's a depth of the color is different. It is lighter, this is darker. Here it is more yellower, it is less yellower. So you should have the similar color, so to understand means same depth, so that you can understand easily. So this is the challenge when you visually observe and when you do the measurement by the instrument. These are calculations we need not to understand more. Now we come to the instrument. There are various type of the instruments. Like some instruments is having single angle on certain angle from the object and the receptor on the different angle. So the receptor is a perpendicular. It is called a 0 degree, and this is the called a some 45 degree. Just a minute. But here you can see your the light source is reflecting into the sphere. Sugato Ghosh sir has explained you the integrating sphere. So the instrument is also having the integrating sphere, where when you click the measurement, the light will first scattered fully into the integrating sphere, and then it falls on the object, and then the reflected light is calculated at 8 degree by the sensor. And the instrument which you have procured is having this angle. So when you click all the light will first is so now we see the instrument which you have procured, what it will give you. In next slide will give you show you the instrument which you have procured it. when light falls on the object,
The CM5 even performs. Anyone can just switch it on and start taking need to bother with a computer. Anyone can just switch it on and start and complete control panel.
those simple. Result. One time you get the different LAB value, second time different LAB value. So that is why we have provided the smallest measuring. What you see, it is around the 30 mm. Simple. We cannot measure less than 6 mm. So you need to consider that whatever you want to measure, your sample size should be minimum 6 mm diameter. If it is less than diameter, what will happen? The sample may go inside and it cannot measure the reflection of that sample, and it also can damage the instrument also. So because so that is a facility it has been given for the smaller size sample and bigger size sample. It is always told that to get the good results of color measurement, you should have the larger sample size. But if there is a constraint, then the makers of the instrument has been provided the smaller size of the 6 mm. Like this, for any size of the sample you can measure here. There is no limitation of the size. But only if there is a small size, then there is a challenge. And you can see here the color has been measured in terms of the L, A and the B. We have already seen what is the how we understand the L, A and the B. So all the color has been quantified in terms of the L, A and B. So as I already explained you, here the maximum size can be measured 30 mm and more than that, and the minimum size of the sample should be 3 mm and more. Yes. And then another thing, we have explained you that this instrument can measure the reflectance on the top port as well as the transparent object also. Although your application is not transparent because dental is very opaque and cannot be used in the transmittance because light will not pass. To measure under transmittance, your sample should light should pass through your sample, because the uh, light will come from this side and it will pass through your sample, and then detector will be from this side. So if it is light is not passing or blocking, then you will not get the results. It will give the error. So this instrument is having the facility to measure the transparent objects also. So like you can measure the liquids, any type of the liquids here. Yeah. So for small size, they have put the smaller measuring area. You also have the smaller area. When you have the opportunity to see the spectrophotometer machine, you can visit and you can see there is a small aperture and the big aperture. It will be selected according to your sample size. Uh, I want to explain about the briefly about the color measurement and the instrument which you have. Thank you so much for your attention, and any question are invited, please. If there is no question, one question, yes, please, Dr. Sujas, you have some question. In the form of LAB, and also if you want to have the spectrum data, you can also get the spectrum value also. Yeah, spectrum value is also available. There is two parts. One is the instrument itself. In instrument you can get the selected wavelength at particular 3 wavelengths, but you also procure the software. In software you get the value from 360 nanometer to 740 nanometer for each measurement in the interval of 10 nanometer, 10 nanometer, 360, 370, 380, like that up to 740 nanometer. You can also get the reflection data, spectral data of each measurement. And duration is? Uh, it does not matter, because you may get the different reflection data. Yeah, there is no chance of the loss, because the measuring area is fully covered. Measuring area you are fully covering by the sample, right? So light is not going anywhere. Light will strike to your object and then come back to the sensor. But the reflection data may change if you have the plane surface or structured surface. Thank you. So madam has asked you one question in skin care, how you can use the spectrophotometer for the quantification. Like this, what we have explained, it's a benchtop spectrophotometer. The sample has to be put on the instrument. The instrument cannot be taken anywhere. But we have the portable instruments also. Like in certain derma case or dermatologist, they are using our portable instrument to check the skin color. See, skin has a certain color, right? If there is changes in the skin color, their LAB value will also change. Fresh skin and diseased skin will have the different LAB colors. Likewise, the cosmetic people who are developing the cosmetic cream, they also want to understand how your skin has become fair. So what will they do? They will first check your skin, then apply their cream, and then they will check the LAB value. So LAB value means your A and B color will be, should be same, but your lightness and darkness, because you want the more lighter color, skin should be more lighter. So your L value should be nearby 100. If your skin is color is showing towards the darker side, then if you apply the color, then your skin should be lighter. It means L should be higher side. So that is how they are using the color measuring instrument on the directly they put the instrument on the skin or hand like that. Another thing, there is now advanced technology uh, called hyperspectral imaging. We have supplied hyperspectral imaging camera into the SRM University, Mangalgiri, Andhra Pradesh. They are also doing the case study on the uh, skin, cancerous skin. How it works, it takes the image, the camera takes the image of the skin. So, like each material has a different spectrum, right? So, if the material is differing from one material to different material, then your spectrum is also different. Like one person is differing another person by the thumb signature. Each thumb signature of the person is different. So likewise, each material has a different spectrum at each wavelength. So they take the image and its wavelength range is from 400 to 1000 nanometer. They take the fresh skin, it shows the certain spectrum, and if the disease is happening or something happening in the skin, then your spectrum is differing. So without destroying your skin, by just taking the image by the camera, they're analyzing. So they are having some study or library that what is the uh, spectrum of the cancerous skin and what is the spectrum of the fresh skin. So how they are nowadays they are doing it. Any other questions from anybody? Yeah, translucent can be measured on the opaque because if you measure in the transparent transmittance, the light should be passed fully. In translucent case, it might happen that light cannot be passed. So you can put the translucent sample on the upper side, reflection side, and you put the some white portion on that of the surface, your object surface, so that the light cannot pass through on the air. Because if it is translucent, some light happen that it may pass through the sample, it cannot come back for the calculation. So when you want to measure the translucent sample, you just put on the reflectance board and cover it by the white tile so that you can get the all the reflection back for the calculation. So likewise, you can measure the translucent sample in the reflectance mode. Reflectance. Transmission is only for when you have fully transparent, you can see through the sample. If you cannot see through the sample and certain things is haziness, then you have to put into the reflectance mode only. So you can use it only in the reflectance mode. Top of the part, you some white ceramic tile you can get put cover on the top of. No, if you put the black tile, what will happen? The light which is coming out, it will be absorbed. It will not reflect. So you will not get the correct value of that color, particular color. Hmm. That can also be done. That is called opacity. Means how opaque is your object is that you can measure over white background, you can measure over dark background, and then it will give you how opaque is your object. Whether it is 80% opaque or 90% opaque, that data also you can get it from this instrument. It is called opacity. And the same thing you can get the different value, different data when you put over the black and when you put the white. Yeah, I think if you put the white background over the top of the sample because the light is coming from below. So the light which is coming out due to the translucent of the sample, it will reflect, go into the white surface, strike it, and because it is a white, nothing can be absorbed, all things will be reflected and come back to the sample and will come into the calculation. You will get the right measurement. So any shop you can go and get the white ceramic tile, like we put on the floor. No, there's a white tiles on the floor walls. So any ceramic shop can give the white smaller white tile.
Thank you so much, sir.
Yeah, please. Sorry, hello.
So can infrared spectroscopy be done on this machine?
Which aspect of it?
Infrared,
No, sir. It is only a
visible
spectrum
light. Okay, okay.
to see the color, because color can be seen only in the visual spectrum. So this instrument is only up to the visual spectrum from 360 to 740 nanometer. Higher range is above 740 nanometers. Yes, basic difference is that SCI means specular component included. A specular component included means whatever the light is coming from the machine and striking to the surface of the object, all the light will be calculated back. So what will happen? There is two type of the surfaces. One is the matte surface and another is the glossy surface. Glossy surface means like a ceramic tile, like a glass. When the any light comes, the incident light, the reflected light is more than the incident light due to the reflection of that surface. So if you see the human by visible eyes, our eyes can adjust. So if you are comparing any glossy surface by visually, you must have observed that person is adjusting his eye angle. Why he is adjusting eye angle? To cut the extra glossiness. So same thing is happening in the SCE mode. When you have the glossy surface, there is a SCE mode. In SCE mode, it is not calculating all the incident light. It is calculating the only light which is not due to the glossiness. Simultaneously, it will strike two beam. One is the calculating the normal reflection, and another it is the light which is cutting the extra glossiness. So when you select the SCE mode, there is one trap is there inside the instrument. If you observe that instrument, the trap comes out. So what will do? It will cut the extra glossiness so that your visual observation and the machine data will match. If it is a more glossiness surface, if it is surface is matte, I think dental is not having much glossiness. So the SCE mode is suitable. But if you have surface like ceramic tile, a glass like this, or plastic surface more glossy, then SCE mode is selected. Otherwise, all the things can be measured in the SCI mode. Any other questions? So if not, thank you so much for your attention, and thank you for your time, and thank you for opportunity for giving me this to present this. Thank you so much.
Thank you so much, sir, for your time and effort. It has been really interesting and informative for all of us. And on the behalf of the institution, I want to thank everybody for your kind attention and all the esteemed speakers. Thank you all so much, and I hope that in future we can use these facilities that our institution has for clinical work, more collaborations and research work. Thank you all once.